right, open up your book to section 9-5. We're on page 459 in your book, and this section here is titled The Ambiguous Case, which is side-side angle. And it's called the ambiguous case here because this scenario here is the one that does not uniquely define a triangle. If you're given side-side angle, we don't end up with a unique triangle. All right, so our objective here is given two sides and a non-included angle. Calculate the possible lengths of the third side of that triangle. All right, so let's start with a couple of examples here. And for each of these examples, we're going to try to sketch the following triangles here. So we're going to give you some side lengths and an angle. In particular, we're going to give you side-side angle and try to sketch the corresponding triangle. Now for the first one here, the triangle that you end up with, if I have A is 30 degrees, side B is 10, and side A is 5, you actually end up with a right triangle, and I'll show you why that's the case here. This will be kind of our starting point here for this, though. So if A is 30 degrees, and we'll make this side B, or that vertex B, and this will be C. So side B is 10, and side A is 5. So if you go back to what we know about a 30, 60, 90 triangle, we've talked about this special triangle many times now. When I look at the relationship between the sides here, the side opposite the 30-degree angle is 1, and the hypotenuse turns out to be 2. Notice that the relationship between those two sides, if I've got myself a 30-degree angle, the relationship between those two sides is 1/2, 1/2, which is the situation I've got here in this case here. That the relationship between the opposite, or the side opposite the angle A, or the 30 degrees, is 5, and one of the sides adjacent to angle A is 10, so that ratio is 1/2. We got ourselves a right triangle is what you actually have here. And what that actually tells me here then in this problem, I'll make that a right angle here. What that tells me in this problem is that if I've got an angle there of 30 degrees and one of its sides that makes that angle, one of the rays there is got a length of 10, then that means that the height of this triangle is going to be 5. All right? But let's play around with side A and see what happens here. So that's what the next few examples are going to illustrate for us. What happens if we change side A? Well, again, let's start off with the right triangle that we had sketched a second ago here. So this is 30 degrees. This is side A, or angle A. This we're calling B, and this we're calling C. Again, we're keeping B 10, but now we're going to make A only 4 units long. Okay? Well, for the work we've already done, we know that the height of this triangle has to be 5. So if I make side B here, or side A here, only 4 units long, when I measure that distance, I stop at some point right here. That's the 4 units. And you can see that my side there is a little bit short. I don't quite reach this point down here. So my problem that I have here is that I don't end up with a triangle. This is no such triangle. Right? I guess I should point that out in the first example that we looked at here. When you have this right triangle, you end up with one triangle as a result. One triangle. Already you can see why this is called the ambiguous case, because in one scenario I've got a triangle, and it's a right triangle. In another scenario, if I make A too short, I don't have a triangle at all. All right, let's look at a couple more examples of issues that we can run into. So it's, again, working with that same triangle that we're talking about, the angle A is 30 degrees, B is still 10, but we're going to change A. We've already looked at what happens if it's 5. We end up with a right triangle. 4, it's no triangle. But again, let's start with our right triangle here that we know. If I make this 30 degrees, and this is A, this will be B, this will be C. Here's our 10, and this is 5. All right, so if we're going to make side A equal to 6, we'll now notice that side A here, it has to be at least 5 to be the height of this triangle. So if I make it 6, it looks like you actually have a couple of possibilities here then. I could have this triangle, I'll do this in blue, I guess, this triangle here, where this is 6 here, and end up with this blue triangle. Or I could have that 6 kind of going on the inside here, maybe. So it looks something like this. And this would be 6. So it looks like I have 2 possible triangles that I end up with then. I could have this triangle that I see over on the left here, and this would be my angle B, or the one that I have over on the right, and this would be my angle B. All right? Let me get rid of this B here. Those are the 2 possible scenarios that I have there. So this looks like I end up with 2 triangles. 2 possible triangles. Again, you can already see the problem here with this ambiguous case. I got a scenario where there's no triangle, a scenario where there's 1 triangle. Here's a scenario where there's 2. And there's one more possibility we should consider. And the last possibility to consider is, again, keeping angle A the same and side B the same, but now let's make side A even longer. So again, let's start out with our right triangle that we started with in this problem. If this is my 30-degree angle, and this is A, I won't label that one B down there, but we'll call this 5. Here's the height of that triangle. And this is 10. Now because A is 11, which means it's more than this side length of side B here, it's more than 10, it turns out it looks like there's only one way I could sketch this triangle then. The 11 is going to have to come out way out here. So I end up with this triangle being the 11. If I tried to do the same thing and wrap the 11 over on the other side like I saw in the previous example, I won't have my 30-degree angle here. So there's only one possibility here that I end up with. This would be B, and here's that angle B that we're looking at. So this is one triangle here. All right. That exactly shows you why this is called the ambiguous case. You end up with all these different possibilities, and the question is which one is the right one. We have a situation where I have one triangle and it's a right triangle. A situation where there's no triangle. Here there were 2 triangles, and here there was just one triangle. So you have to be a little bit careful about that side that's opposite the given angle. Depending on its length, then it depends on which one of these 3 scenarios we will run into. All right, so how do we handle this? Well, if we're given this ambiguous case, side-side angle, then the problem that we're seeing is that you run into these 3 scenarios here. Given 2 sides and an angle opposite one of those sides, so side-side angle, there could be either 0, 1, or 2 possible triangles. That's exactly what the previous examples have illustrated for us. And that actually wraps up all the possibilities that we have here. You have either 0, 1, or 2 possibilities. We looked at what happens when you make side A too short, when you make it exactly the right length to get a right triangle. What if it's longer than that, but shorter than the other side that we're given? And then the last scenario is what happens if it's longer than the other side we're given. Those are the possibilities there. Well, how do we handle this, and how are we going to deal with solving problems that have side-side angle given to us in the problem? Well, here's the solution technique that we're going to use. We're going to use the law of cosines for the following reasons. We're going to use law of cosines to solve these problems. First of all, when you use law of cosines to do it, you're going to produce a quadratic equation. We'll go through an example, and you'll see that here in just a second. But it will produce for us a quadratic equation, which, of course, that means there's going to be a little bit more work to solve that quadratic equation, but I'll have a quadratic equation. The good news for us is we have a way to solve quadratic equations known as the quadratic formula. So we're going to just run this through our quadratic formula to solve this equation. The good news for us there, when we run this through the quadratic formula, I'm going to get either 0, 1, or 2 solutions when I run that through there, but in particular, we're only worried about the positive and real solutions. So you'll still have either 0, 1, or 2 positive real solutions. Anything that's obviously imaginary, we're throwing out. Anything that's negative, we're throwing out. We're talking about side lengths of a triangle, so we're going to throw out those other scenarios there. It's positive and it's real. You'll get either 0, 1, or 2 solutions. And the nice thing about that is that corresponds to the number of triangles that you have possible. If you get 0 positive real solutions, then there's no such triangle. That's the scenario where we made A too short. If it turns out there's 2 triangles, then that was the third scenario we looked at. What happens when A was between whatever the height of your triangle is and the other side given. And then when there's 1, there's the 2 possibilities. It could be a right triangle, or it could be that that third side is bigger than the other side given. All right, so quadratic formula, using law of cosines, that'll be a nice way to solve this. Let's go ahead and try that out. Take a look at example 1 there on page 459. They give us triangle XYZ. In triangle XYZ, they say X is equal to 50, Z is equal to 80, and angle X is 26 degrees. Again, just like we've done for all of the previous problems, I'd recommend you draw yourself a triangle, label it with the sides here. So we've got X, we've got Y, and we've got Z. And then go ahead and fill in the numbers that they've given there for us. So they told us that angle X is 26 degrees. They said that the angle Z was 80 centimeters. And they told us that X was equal to 50 centimeters. Now, I've sketched it this way. It could be that this is a right triangle, so there's only going to be one solution. It could be that there's also a solution that lies, if I draw it this way maybe. Okay. I do know that there's not going to be the third solution possible there where there's not this inside, because of the fact that I've got a value here that's less than 80 for the other side here. Okay, this is narrowing it down for me, but I still don't know which one of these 3 it is, so let's see by using law of cosines what our solution will be. Now again, when you set this up with law of cosines, you got to look at the angle you're given, and the side opposite of that goes on the other side. So it's 50 squared is equal to, it's going to be let's call this y squared. So y, oops, not y squared, but y. In my law of cosines, it's going to be y squared. Y squared plus 50 squared minus 2 times y times 50 times the cosine of 26 degrees. I suggest that if you look at that, you're going to see a y squared term in there, you'll see a y term in there, and there'll be a term that has no y in it. That is a quadratic equation. Let's just rewrite it so it looks like that. Oops, this should be 80 here, right? 80 squared and 80 there. All right. All right, so let's go ahead and solve this. But I'm going to move the 50 squared to the other side. So we'll have 0 is equal to y squared. I'm going to put the y term here next, and I'm going to write it as minus 2 times 80 is 160, cosine of 26 degrees. And then I'll put the y at the end. So I've got a constant times y. And then I've got the plus 80 squared, and I'm going to subtract the 50 squared to move that over to the other side. All right, so I've got a quadratic equation. And again, I still don't know how many solutions I'm going to find from this. It could be that there's no solution, it could be that there's one solution, or it could be that there's 2 solutions. Again, the sketch that I have above doesn't quite tell me that. I do know that I can eliminate one of the possible sketches that I had in the beginning, but I don't know about the other 3. So grab your calculator and let's just run this through your quadratic formula on your calculator. All right, so we grab our quadratic formula on our calculator. If you don't have one, you're going to want to get a quadratic formula program. You could also, I guess, use the solver on your calculator, or even graph these to find solutions too, I guess, but probably a quadratic formula program will be nice. So I have one here that I'm going to plug in my 3 coefficients here. So it's 1y squared, so a is 1. And then I can actually type this in terms of cosine here. So it's a negative 160 cosine of 26, which you want to make sure that you are in degree mode here when you go to do this calculation. So make sure that it's in degree mode here, I guess, before you start this. If it's not, by the way, I should show you that. If you go into your angle menu, second angle, there's a degree mark here. And that will force it to use degrees when it does this calculation. So if you start this out and you're not in degree mode, this would be one way to fix that, is just force that calculation in degrees. And then finally for C, that's the 80 squared minus the 50 squared. And you can just type it in just like this. It'll crunch that and store it to the right variables for me and run that through my quadratic formula program. So there are the two solutions, 107.542 and 36.264. So it looks like there's two solutions. I got both of these are positive. They're both real answers, so both of those are potential solutions there for us. So what does y equal? Y is equal to, I'm going to write the smallest one first, 36.264 or 265. And the other solution is 107.542. All right. Make sure that we include units if we have them. We do have units, so I should add the units on there. Those are both in centimeters. Centimeters, I'll just say, or this in centimeters. Now that gets us the value of what side length y is equal to. If you wanted to find out what angle z is equal to, you can now use law of cosines to help you find out what z is equal to. Realize that the sketch I've got here, this is one possibility for z, and the other possibility for z is this angle here. But realize that those are actually supplementary angles there. Okay? It turns out that this is 50. What you have here is really an isosceles triangle. This right here, although mine doesn't look isosceles, but it should. This is an isosceles triangle. So these angles right here are congruent, which means that this guy right here is the supplement to that angle. So really, I only have to do the work to find one, and then I can use the supplement to find the other one if I want to find my angles there. They didn't ask us to do that in this problem. They just said to find the length of y. But if you wanted to also find your angles, just realize you got two triangles you're working with here. So it's not sufficient just to find one value for z. You have to say, well, for this given value of y, for the 36, this is the value of z we'd end up with, and the corresponding value for y. And do the same thing for the other side length of y. Find the angle y along with the angle z. That right there is the end of this section. Section 9-5, the ambiguous case.